All right, so in the 1860s, Mathieu introduced or discovered these new simple groups. They were rather large, and they were sort of exotic things. And perhaps their significance only became established much later in the 20th century due to essentially coding theory, the development of coding theory in the 40s and 50s. So in 1949, Golay discovered an important code. The Golay code was discovered. This is a certain code called a 2312 code. What does it mean? It means there are 2 to the 12th, that's 4,096 binary sequences, okay, of length 23. So each one is a sequence like 1, 0, 0, 1, 1, something like this. Imagine going on to length 23, and there are 2 to the 12th of these. Okay. And they have a rather important, interesting algebraic structure. It turns out that they're a lattice. So that if we're working in the vector space of a field of 2 elements, only just 0 plus 0 and 1, that the computer scientists like, with 23 elements, think of this as a vector in a 23-dimensional space over F2, then these 2 to the 12th vectors have the property that if you add any 2 of the vectors, you get another one in the list. It's like a span of some vectors. It's like a vector subspace, in fact. Subspace of this 23-dimensional space. And what's interesting about these things is that each, or any 2 of these, any 2, differ in at least 7 places, or 7 digits. So if you compare any 2 on this list of 4,000 strings, any 2 of them are different in at least 7 places. So this is a code. That means that if you have a message and you can associate to parts of your message one of these strings, then if you send this string off in some noisy communication channel where there may be some errors creeping in for whatever reason, if there's 1 or 2 or 3 errors, you'll be able to say, aha, that this is not actually one on my list, but it's pretty close to this one. So it probably is this one that was being sent. So you can tell whether there have been errors, and you can, in fact, correct errors by using these code words as the things that you send and transmit back and forth. All right. So this is a rather sophisticated version of a code. There was a simpler version that's much more familiar called the Hamming code, which is much smaller, which was also developed around the same time. The significance is that it was realized that the group of symmetries of this code was one of the Mathieu groups. I think it was probably M23. So M23 is the symmetry group of this code. So that's a kind of a remarkable connection. And in fact, the M24 is also the symmetry group of a very closely associated code called the extended Golay code. So these groups are curious objects. They're somehow associated to things out there which have a lot of symmetry, which are not so easily visible, but nevertheless, once you find them, like Golay did, they can be actually quite useful. Although we have to go to 23 dimensions working over F2 in order to see this. All right, so that was interesting, but the story got even more interesting when it was realized that in order to study finite simple groups, in order to understand them properly, you really needed to appreciate Sophus Lie's theory of continuous groups. Okay. So here, Sophus Lie enters the picture, who was a brilliant geometer and a Norwegian who ended up spending quite a lot of time in Germany and in France, and ended up being a close associate with Felix Klein and had a lot to do with Felix Klein. And he developed, he was actually originally interested in differential equations, and he actually wanted a Galois theory for differential equations. He wanted a Galois theory. He wanted to do the same thing for differential equations as Galois had done for algebraic equations. That was his aim. And as he was developing that, he realized that there were these continuous groups that played an important role, kind of analogous to the Galois groups, the finite groups of Galois theory. And so he ended up single-handedly developing this theory of groups, which is now called the theory of Lie groups. And there's some closely associated objects called Lie algebras, also named after him. Okay, and the basic thing, I suppose, is that these are continuous groups, not just finite groups. So what are some examples? Well, one example is rotations of a circle. Sort of going back to the regular polygons, but thinking of a polygon with, in sort of in the limit, which has many, many sides, it becomes a circle. In this case, the symmetries are just rotations, so given any angle, theta, you can rotate by theta. In this case, the rotations are often called SO2. They are often described in terms of cosine theta, sine theta, minus sine theta, cosine theta, with irrational parametrization, or better, with a rational parametrization, 1 minus t squared, 2t minus 2t, 1 minus t squared, all over 1 over 1 plus t squared. It's a rational parametrization of these rotations. So basically, for every angle, there's a rotation. And so topologically, this group looks like a circle itself. The group is really very much the group topologically of a circle. So that's one simple example. A more sophisticated example is when we look at rotations of a sphere. That's called SO3. This is rotations of a sphere. So if we have a sphere, then we can rotate it. And the way we do that is we fix an axis. So we choose some axis going through the center. And then we can rotate by some amount around that axis. If you think about it, well, this is kind of a two-parameter family of axes, because the axis could be pretty well anywhere on the sphere. There's a one-parameter family of rotations. So altogether, this is really a three-dimensional kind of object. This is a three-dimensional Lie group. The fact that it's a group actually requires a theorem of Euler. So Euler proved that the product of two rotations is another rotation. So if you rotate a sphere about some axis, and then you rotate it about some other axis, that combined rotation is really a single rotation about some third axis. So that's an example of a three-dimensional Lie group, and it turns out also to be a simple one. Sort of in the family, or in the world of Lie groups, it's a simple group. It doesn't have any normal sort of Lie subgroups. All right, but the theory is much richer than that, because we have linear algebra to help us. And so there's a rich family of things called matrix groups. Okay, so everything inside this big group GLN that we've already talked about, the group of all n by n matrices. So inside that we can find simple groups, simple Lie groups. Well, things form SLN, which satisfy the condition that determinant of M is not just equal to something non-zero, but actually equals 1. If you restrict to determinant 1 matrices, then you get a subgroup inside GLN, and that subgroup turns out to be a simple group. And then there are orthogonal matrices. The orthogonal group, consisting of orthogonal matrices, they satisfy the condition that M times M transpose is the identity matrix. So-called orthogonal matrices from a linear algebra. And then there's some groups called, so these are orthogonal. This is sometimes called special linear group. Special linear group, the orthogonal group. And these ones here, the sp2n, these are sometimes called symplectic matrices. They have the property that M times omega times M transpose equals omega, where omega is, okay, it's a 2n by 2n matrix, which has the identity here, zeros there, and minus the identity there. So this is related to the theory of symmetric bilinear forms. Here's a non-symmetric bilinear form, skew-symmetric bilinear form, and these are the matrices that preserve that skew-symmetric bilinear form. That's called a symplectic matrix. And they ended up becoming very important in classical mechanics and physics. So these are families of simple Lie groups. Okay. And then in the late 19th century, a fellow called Killing came around and made a beautiful classification, and he discovered that he classified simple Lie groups. So basically there are these infinite families just that are on that list. The previous plus 5 exceptional ones. And these exceptional ones are E6, E7, E8, G2, and F4. Those are their names. They are remarkable objects that somehow are connected with symmetries, higher dimensional symmetries, which are not belonging to any kind of family. They're sort of exceptional. They're just sort of one of them out there. They're just out there in the mathematical universe. And Killing discovered these things, and they have turned out to become very interesting objects of study in the 20th century. So modern physicists are very keen about trying to understand what the symmetry group of the universe is, which involves the 4 fundamental forces and gravity and quantum mechanics and so on. So they have all these various theories, and they are starting now to look at some of these groups, especially E8, with the idea that maybe these groups can be ultimately explaining what's going on with modern physics. So people are taking them more seriously. They're not just entirely exotic things now. But in the 20th century, it became clear that these were sort of related to the hypercomplex numbers of Graves things we called octonions. So remember that we had complex numbers, and we had quaternions, and we had octonions. Well, it turns out that these groups are somehow associated to geometry over the octonions in some fashion. That only became clear with many decades of work. So this was a great kind of advance by Killing to really bring this theory of simple Lie groups into very beautiful focus. And then it became clear to the finite group theorists that this was very useful to them. All right. So once you have a Lie group, as matrices, you can change the field. So where previously we may have been just working with rational number entries, once you have, say, a group of orthogonal matrices, you can ask, well, what happens if we work over a finite field? If the entries of the matrix is from, say, Z7, then we get a finite group, and it turns out that new simple groups were derived this way. So you could take these classical Lie groups and replace the fields with finite fields, and you often get finite simple groups. So with finite fields, we get, say, finite simple groups of Lie type. And so until the 1960s, in fact, this was essentially the list of finite simple groups that people had discovered. There were the alternating groups. There were the groups coming from projective geometry. And there were these groups of Lie type, finite groups of Lie type, plus the 5 Mathieu groups. Okay. So the Mathieu groups were kind of exceptional. They didn't, or sometimes called sporadic, they didn't fit into any of these other families, into this pattern. They sort of just existed out there independent of the other ones, much the same way as these guys sort of are out there independent of these families. Okay, so then in the 1960s, though, the story got much more interesting and involved. And one can spend many lectures, I suppose, on the history of this. Maybe at some point I will lecture some more on this. But so in the 1960s, new finite simple groups were found. So this started, I think, by Jankel in 1965, who found 4 new simple groups, now called J1, J2, J3, J4. And then John Conway, who was the discoverer of the game of life, discovered 3 new groups, Conway groups. And it turned out that these were also somehow very closely connected to a remarkable lattice called the Leech lattice in 24 dimensions. Somehow nature has some affinity for 24 dimensions. It's kind of an interesting dimension. So the Leech lattice is some other remarkable structure, and these Conway groups were somehow connected with them. And some more were discovered, but eventually in about 1973, Fisher started to suspect that there was a yet bigger group out there, and he could see that there was these indications that there should be some group, so people started looking for this group, and eventually Greiss was able to put it together in 1980. And so this is a group called the monster group. The monster group, M. How big is it? It's a group of size about 10 to the 54. It's a pretty big thing. And you can realize it can be realized as a subgroup of matrices of GL 196883. So 196,883. Take matrices of that size, you can find this monster group you can find these 10 to the 54 elements inside these this GL of 196,883. But it turned out that this number, remarkably, was observed by John Mackay, Canadian mathematician, to come up in a completely different context, in the context of modular functions. Connections with modular functions, which is basically some kind of complex analysis. And when that was investigated further, it was discovered that there was this remarkable deep connection and mysterious connection between the monster group and, well, a lot of other things. Okay? So in particular, the E8 somehow was involved. This Leech lattice that had been connected with the Conway groups was involved. And then other things became involved. Modern physics had a lot of input, string theory, and theory of infinite dimensional Kac-Moody-Lie algebras. So a lot of things were coming together here, and sometimes this is called monstrous moonshine. This sort of phenomena that there are all these remarkable connections between these big, seemingly quite different things. And it was, and is still, a subject of quite a lot of investigation. So to finish the story, we can say happily that the search for finite simple groups with a monster came to a close, in the sense that at least we had a list of them all. But it turned out that proving this was far from easy. So the classification of simple groups is surely of finite simple groups. Surely the largest mathematical undertaking in history, okay, and involved dozens of people, tens of thousands of pages of journal articles. And eventually, the classification is roughly, there are these infinite families that we've talked about, namely the alternating groups, the projective linear groups, the groups of Lie type, plus 26 sporadic groups. Starting from the Mathieu groups all the way up to the monster. So there were these 26 weird ones, or not weird, but sort of didn't fit into anything else. Janko groups, Conway groups, the monster group, and some other related groups sort of related to the monster. So this was a tour de force of mathematical research and collaborative effort that was really awe-inspiring, I think. And many people were involved. And it's still in the process, really, of being written up. So, people trying to simplify, trying to get all the facts together, try to write it up in a coherent whole so that people can look at it and judge that it's actually correct. Because when something is this big, there's always the possibility that there's some little error somewhere, and maybe there's a 27th sporadic group out there somewhere actually that somehow slipped through the net. Probably not, but there's always this slight possibility, I suppose. So this is a very interesting story, starting, of course, in the 19th century, and you can see that it's been a main driver of a lot of 20th century research and connecting to a lot of things, including physics. So it's an interesting chapter of history of mathematics, which probably I should say a little bit more about at some other point. All right, so we'll leave the course here for now.